With that, it's my pleasure to introduce our first keynote speaker of the day, Yan Liu. She is a professor in the computer science department and director of the Machine Learning Center at the University of Southern California. She received her PhD degree from Carnegie Mellon University. Her research interests include machine learning and its applications to climate science, healthcare, and sustainability. She has received several awards, including an NSF Career Award, Okawa Foundation Research Award, New Voices of Academies of Science, Engineering, and Medicine, and a Best Paper Award at the SIAM Data Mining Conference. She serves as a general chair for the KDD 2020 and ICLR 2023, and program chairs for WSDM 2018, SDM 2020, KDD 2022, and ICLR 2022. With that, please join me in welcoming Dr. Yan Liu.
Thank you. Thanks a lot to James for the introduction. And also, I would like to thank the committee for inviting me. So I'm really excited and honored to be here. In yesterday's event, I was able to actually meet a lot of researchers and also leaders in different fields. And that's really what this transportation area is about. It's a multidisciplinary area where it consists of all the efforts from experts in different domains. And in yesterday's tour in the lab, I was also able to see next generation type of car repairing system that's obviously consisting many different areas. As for myself, as a researcher in machine learning, specifically machine learning and AI models for time series, I started to look into the area of transportation when there was a big data. So you might notice that probably 10 or 15 years ago, we started seeing that there's a large amount of data publicly or privately available in this particular domain, where we get sensor data or GPS data. This gives the people in machine learning and AI a really well playground for us to do research. And then the other thing is because that after moving to Los Angeles, I realized that literally traffic and transportation is an essential part of our daily life. I get used to the situation where that we will start all the talks like 10 minutes late by the time, and getting anywhere from point A to B literally takes at least an hour. So that's definitely from personal perspective, this is a really important topic for us to work on. And when we have lots of data, and also with the development of the deep learning and AI technologies, this literally spurred a huge amount of interest and also a lot of exciting work followed after that. So our journey started with this particular paper where we're trying to develop this first generation deep learning model for traffic prediction. In this particular model, we were using this diffusion convolutions on the graphs to model the spatial dependencies, which is essential for spatio-temporal forecasting. And we also use the so-called augmented recurrent neural network, one version of the neural network, so that they will be able to model the temporal dependencies. With both the diffusion graphs and also the recurrent neural network, we're able to build a very successful model to provide a very, basically achieve the state-of-art results on traffic forecasting. So in this data set, both the data from Los Angeles and also in the Bay Area, our method, which is called DCRNN, was able to achieve the best results basically across all the different methods at that time for both near-term prediction and also long-term prediction. Then after I spent my sabbatical in Didi, that is the Chinese Uber, we started working another essential problem for ride sharing, that is so-called the demand forecasting. Basically, they were interested that how much demand of ride shares request from one location to another location at different time of the day. So in there that we have to consider quite a lot of things. That means that for the location information, for different locations, there's actually different type of relations among them. For example, they could have actually the proximity, the spatial proximity. Each location may have different type of functionalities or the connectivity in terms of the road network. And we want to take into consideration of all of them. And that is why in this work that we developed the so-called multi-graph convolutions, so that we'll be taking into consideration jointly all these different properties of the locations so that we can make accurate predictions. So in this particular work where we actually performed the prediction for Beijing and also Shanghai, that is two largest cities in China. And then our approach, were able to achieve the best prediction performance comparing with the state of art at that time. So after our work and many others, the area started booming, basically that we're able to attract so many researchers in the area. And every year right now, even in the field of machine learning itself, there are probably hundreds of papers or even thousands published a year on this particular topic. And then there are also many models have been developed accordingly. So it was so hard for me to keep track on all these models. So I did myself a favor, and also hopefully that helps you in a sense to see what is actually happening in this area in the past 5 years. So after this graph convolution neural network was applied to transportation and traffic area, we see that a wide range of different type of models. For example, the most popular one is the so-called transformer-based approaches, and then there's still different versions of the graph convolution neural networks. And then recently, people started to look into the self-supervised learning or unsupervised learning approaches. And then I would say that last year or a few months ago, people started to looking at, again, the linear simple model to see how well this can actually work for different type of time series forecasting tasks. So what we did as a first step is that we want to see, hey, how these methods perform actually on the same playground. So what we did is that we apply all these different type of methods to this benchmarking data sets is available. So it's a little bit hard to see in this particular screen, but basically that we test the data sets on traffic applications, but also in other applications such as energy, New York taxi data, electricity, weather, and etc. But across the board, what we see is that it seems that the transformer-based approaches were able to perform relatively well for the near-term prediction. And then for long-term prediction, then both transformer and also the linear model seems to work well. An explanation for this is that because the long-term prediction is such a hard problem, therefore sometimes it is challenging for all the methods, and therefore even linear model can sometimes work the same or similarly as the transformer-based approaches. So when we work on these different type of problems on these so-called artificial data sets, we were very happy that there is a good breakthrough because of the results of the improvement over the years. But then when we started working with the real experts in different type of areas, we noticed this thing. That is, when we publish research papers, the model looks so good and they were able to get really nice predictions. And then when the domain experts get our prediction results, it's probably look a little bit different. So we were trying to understand, what actually causes this and what essentially are the problems that we need to address. So I summarize that I think there are two types of problems or challenges we need to address. The first one is from the challenges in the real-world application. Whatever we see in the research papers is that the actual data sets look so nicely formatted, and there is no missing data. Everything is just clean. But in the real application, what happens is that you get a lot of missing data, and there's noise in the data because of the sensor issues, or there's irregularity. That means, that the sensors are broken, or maybe, that there were some issues with the way of the data was collected. The data essentially coming from multiple sources. There's also a lot of description of the data that the domain experts would like to use them. So as we can see from the data perspective, they're totally different from what we actually see in this really nice formatted Excel sheet that we worked on. The other challenge that we see basically for all these AI and machine learning models is that first is that this is actually very data intensive. That means that in order for the model to actually work very well, we need large amount of data to train the model. What possibly could happen in practical application is that you will be working on some road or some particular situations where there's a limited amount of data, or sometimes there's not much data. Can you make any predictions about that, right? I mean, it's very difficult for these data-driven approaches. The second thing is that it's actually very human efforts and also computational intensive. Because for the example I just gave you, for each particular task, for example, traffic forecasting, we need to have a predictor. That means that we have to have probably at least dozens of researchers working on the topic and then developing a model. And then for the demand forecasting, there's another set of researchers working on the problem. I'm also at the same time working with researchers in Google. They're interested in the OD estimation. Okay, that we have to look at another set of papers, another set of models in order to make the algorithm work for that particular application. So that means that all the models have to be specifically developed for each of the tasks that we work on. And that is obviously very labor extensive. On the other side, for each model, you need to train them and you need to actually build the models. And that, again, taking a lot of time. Talking about how expensive GPU these days can get, it's really infeasible in academia to work on any data-intensive research problems anymore. So that is really also a lot of challenges in there. The next one is also extremely important. When I talk with traffic or transportation experts, the feedback we keep on getting is that, there's a lot of domain knowledge, especially this physics domain knowledge that were actually incorporated in the simulation model we built. But in your data-intensive approaches, that is actually not much they were considered, but we really want to consider them and taking advantage of them. So all these challenges, spurred us to actually look into new frontiers and research in this particular area to see what would be actually the new research area for the next 5 years. And when we look at what has happened probably in the past 1.5 years, there has been a huge interest and a lot of research studies that building foundation models for both the text data and also the images. Starting from the release of ChatGPT to later now we see DALL-E and we see Sora right now, that these are all relying on the so-called foundation pre-trained models so that we will be able to actually learning the effective representation of these data, and then we will be able to provide a general purpose models for generating text or images and videos and etc. And therefore, starting from last year, that there has been a huge interest in the community to see if there is any way we can build this foundation model for time series and spatial temporal data as well. And that, I would say that it started a new era of time series modeling. And then in this particular line of research, when we look at building foundation models for time series and spatial temporal data, we notice that there's actually quite a few things that we need to look into. The first, obviously, is that we notice on the data level, as I mentioned, there's all these challenges, and especially these are the unique challenges that we need to look into. For example, multi-resolution, missing values, multimodality. These are the data challenges that we need to address. And then in the intermediate layer, that is, we're trying to build a machine learning model. As I mentioned, there's all these model challenges as well. And therefore, that we want them to take into consideration of the physics knowledge. We want them to be actually a general purpose, that is a foundation model. And then we obviously need to look into consideration of the actual causal relationships instead of correlations. And then a lot of the data, actually in yesterday's keynote talk, this was also mentioned, that is basically, there's a lot of data actually distributed across different areas and different sources. And there is a lot of them, for example, the trajectory data that is actually has to be preserving the user privacies. And therefore, how we will be able to actually doing privacy preserving machine learning and AI models, that is another challenge. And last but not the least, we also want the model to be interpretable. Both we're able to incorporating the physics knowledge, but also we will be able to actually making the final predictions interpretable for the non-machine learning experts. So this is literally like a huge task. As we can think of this is going to take a lot of research work, probably years of research work, in order to achieve the goal. But I would say, right now the area moves really fast, and that is really what I want to share in today's talk, how the development in this area has actually gone through in the past, I would say probably the past 6 months. That has been a lot of really interesting research work. So in this particular work that published by Alibaba, and they proposed a so-called model that is called LM4TS, that is a large language model for time series. They actually exploit this particular idea of this general purpose time series foundation model. With some architectures based on transformer, they were able to actually achieving good prediction performance and in many different type of tasks. For example, in either short-term forecasting, long-term forecasting, imputation, anomaly detection, classification, and many others. And then this gave us a lot of hope in terms of following the footsteps of building ChatGPT for text, whether that we will be able to build this foundation model for time series. In order to do so, there's also a lot of basic tasks that we need to solve. The first one is that time series different from text. We need to consider a little bit of the representations for sequence, for example, that whether we want to actually consider different type of patches or convolutions. People have looked into patch, like the patch TST, or 2D com, or positioning embedding, and etc. Once we get the pre-processing stages, then we also need to look into the backbone of the model. As I mentioned, there's so many different type of architectures have been developed in the area. Which model, which one that actually we should use is not clear. For example, that we examine the specific approaches that it seems that transformer-based approaches that actually can achieve very stable and robust results, and that's what we actually build on. And then all these challenges, as I mentioned a little bit, that they have to be trained general purposes for all the different tasks, and also we need to consider the distribution shift. That is a term we use in machine learning, but basically the idea is that the time series or the traffic situation will be dynamic, and therefore the distribution will changes all the time, how we will be able to actually adjust them. For the real model. And sometimes we would like to take into consideration of the textual information. That means that, there's text data or maybe images. We want to consider them together with the time series data signals that we receive. So these are the nice challenges that we have to work on for our research. So in this particular work that we just presented in iClear, that is one of the top conferences in deep learning, we were able to achieve a good step toward this particular goal. So we call this particular model Tempo, that is the prompt-based generative pre-training model, pre-training transformers. We shall name them as Tempo. This is actually addressing very interesting task. That is, we're trying to say, hey, given the observations of the timestamps, that we want to actually making predictions and building this foundation model so that we will be able to actually making predictions for the next K timestamp. And then one major thing that we want to look into is that we want to get data across all these different domains. The things we talked about, we were able to get data from transportation area. We're able to actually get data from climate. We're able to get data from electricity, from power, and many other time series data. We're going to train them all together and building this one unified model. And the target is that we assume that when we're making predictions, we will not have access to the data that we are interested in predicting. For example, that when we build a model trying to make predictions, for example, for transportation, then we do not assume that we have access to this data. And then we're going to making predictions just purely based on the foundation model that we build. And then the other thing is that this is typically known as zero-shot learning in machine learning, but in the naive term, as I mentioned, basically, we do not assume we have any training data for the target domain. And then obviously the key challenges, as I mentioned, is that how we will be able to actually building and adapting the trained model for across different domains to effectively handle the time series data. And then capturing the intrinsic attributes and features, properties such as trend and seasonality, and then generalizing this to the new domain, and then at the same time, naturally taking into consideration of the contextual information. So there's a lot of goals that we need to achieve. So this is basically the architecture of the proposed tempo model without looking into the key components, which is relatively complex, but I want to just highlight some basic ideas. So the first one we want to take into consideration is that we literally need to learn across different domains, and obviously for data from different domains, we actually are going to have different type of trends, seasonalities, and residuals. And therefore, one key component is that we're going to actually doing the decomposition, where we'll be able to actually perform a decomposition for all the input time series into trend, seasonality, and residue. And because we're going to do the window-based approaches and sliding window, and that's why in the end we will be able to get a time series in signals for trend, seasonality, and residue as well. And once we get that, we also have the so-called prompt design. This is the prompt module. This is taking into consideration of the development of the large language model. We want to actually give prompt to this module so that we'll be able to generalizing this input vector and the embeddings if we put the data as a prompt into, for example, ChatGPT or other language models. Once we have these two types of information, we're going to concatenate them to the next block. And then for the next block, what we're going to do is on the bottom left, right, we're going to input the transformers, and hopefully they will do their magic in there. And at the same time, there's also all these modules so that we'll be taking into consideration of the efficient distribution adaptation using the low-rank adaptation and also component-wise output and combinations so that hopefully they'll do their magic to learning the effective representations across all these time series. So this is, the basic idea of this model. There's also this theoretical analysis and some of the particular embeddings that we need to link into consideration, especially if we want to get access to the textual information. So I'm not going to the details. Hopefully you get a basic idea of how the architecture will look like. Next, I'm going to quickly show the experiment results. So the setting, as I mentioned, is basically we're interested in performing the so-called zero-shot learning. So in all these tables, you see basically what we're going to do, what we did is that if we're interested in making predictions for electricity, then we're going to use the rest of the data set to build the so-called foundation model, to build the tempo model, and for other comparisons of the baseline model, and we see how they actually perform. So in here that we compare tempo with the GPT-2 and also T3, that is another version of the large language model, and obviously comparing with all the existing state-of-art methods for time series and spatial-temporal forecasting. So across the board, basically, Tempo was able to achieve the best prediction performance for the zero-shot learning cases across all these different data sets. And then the other thing we want to actually see is that how does this prediction performance look like for building a model using the training data sets in that particular domain. And this is what is shown in this particular slide. So basically for our tempo model, we literally are zero shot. That means that we do not have access to any of the training data in that particular domain. And now we gave these state-of-art models the training data in that domain and to see how far away we are from there. And then in this prediction task, where this is for energy data set, across all these different horizons, 96 steps, and then to 720 steps for longer term prediction, we can see that our tempo model were able to achieve similar or sometimes even outperform the state-of-art model, even though the state-of-art model were able to have access to the data in that particular domain. So these results are really encouraging. That means that there might be some hope that we will be able to actually achieve a universal and general purpose foundation model for time series forecasting as well. And then the other thing that I mentioned a little bit is that we also want to take into consideration of text information. This is especially true for some particular domains. For example, for financial application, there are many news and reports have been produced together with the stocking price. And therefore, that we created this particular data set ourselves. We call this time series enriched text segmentation by ChatGPT data, where that we're able to get access to the stock, in this particular case, it's literally the so-called quarterly EBITDA data explained by the financial experts is actually the interest, tax, depreciation, amortization for the S&P 500. And then we were able to use ChatGPT to generate a text summarize for all the news and reports within that particular time period. We try to be careful a little bit with the data leakage issue because sometimes, you know, that maybe the news already included the stocking price, and therefore that we have to have a nice cutoff when we process the data. And then the other data set we collected is the social news data. We get the data from the GDAL, that is the Google project, where they were able to get all the news, especially that is popular on social media. And then we're interested in predicting the number of news in the future timestamps on that particular topic. So again, this is going to be both the time series data together with the text data. And then this is the prediction results. When we were able to incorporating both the text data and time series, comparing with others, for example, Llama and also GPT-2, and many other, BERT and T5, these are all the large language models, and also with the existing time series model without getting access to the text data, we can see that we definitely were able to get a good improvement comparing with using time series only, and also that comparing with other approaches for the large language model, we were able to get better results. So this is also very encouraging. That means that we might be able to learning a good representation between the text and time series so that we will be able to leveraging the contextual information to help us making the prediction. So just summarizing this a little bit for this tempo model, where we're able to propose this architecture so that we can leveraging the unique data properties across many different domains. And then we have the self-prompting module so that we're able to take into consideration of both the time series and also the textual information. The zero-shot forecasting results are extremely encouraging. And then for the next timestamp, what we're doing is that we're going to look into more components. As we speak, we have this particular paper that is due today at 4 p.m. Eastern time, where that we build this generative model based on diffusion transformer architectures, so that we'll be able to actually doing a good alignment between the text and the time series data, as what the Sara did for the video generation. At the same time, for the longer term, we're also interested in not only the tasks that are relatively simple, for example, forecasting, anomaly detection, classification, but we might be able to actually making inference and doing knowledge discovery. For example, that we might be able to answering complex questions, like what the the ChatGPT does. For example, like tell me, okay, how I will be able to actually improve the traffic in the Detroit area. This is consisting like a very hard inference in the sense that this particular task not only involving simple forecasting, but also that we have to decompose the problem into a set of individual questions. And then once we get the solutions from individual questions, for example, let's take a look at the current traffic situations, right? And then is there any way that we'll be able to actually changing the traffic light control systems, and then how we will be able to actually doing the optimization of different traffic light across different regions of the Detroit area. This usually has to be conducted by the domain experts by each step of the process of research and study. But now enabled with the ChatGPT inferencing technologies, there might be a way that we're able to actually speed this up and also streamline the processes. So I would say that means that for further inference and reasoning, there will be a long way for us to get there, but at least there will be some really encouraging results that we see, at least by the ChatGPT, where they're trying to solve some of the very complicated mathematical equations and etc. So I would say that in the past 6 months, that is when I was feeling the most nervous throughout my whole career, in the sense that I see there's a huge tsunami of the overwhelming waves in these different type of AI machine learning model, especially the foundation models, and thousands of papers published in this area, spurring a huge amount of waves in the current research. But at the same time, I would say that this also means that there's going to be a huge opportunity for us to solve many challenging problems that we may not necessarily be able to solve using data-driven approaches only or using the model-based approaches only. So from that perspective, there's going to be a lot of changes in the particular domain that we're interested, both in AI machine learning model and also in the application area. So with that, I would like to say thank you for your attention. And also, this is my group who has been working really hard and who some of my team members were actually put all-nighter for last night. And then all the funding agencies and also the collaborators that we have been working on this project. So with that, I'll just stop and welcome questions. Thank you.
Thank you for the wonderful talk. I have a question about external data impact. Just like congestion might be different in Michigan versus Minnesota, did you look at the impact of external data or RAG on the impact of the forecasting for the time series?
Yeah, so I think this is a really good question. Basically, this is known as the transfer learning in the machine learning domain. In the previous generation, that many different models have been developed so that we will be able to learn from the data, for example, in Los Angeles areas, and then adapting this to, for example, the Detroit areas. So in this new version of this foundation model, basically that either the data from a different area would help, but also that the regions would help, but also the data from stock price may help you making predictions for the area of traffic situations in Detroit. So that means that now that we will provide a holistic mechanism approaches so that we can take into consideration of any information in the data and then helping our target domain. I didn't have the time to look actually talk about fine-tuning. That means that for each specific domain, once that we are interested in making predictions with access to the foundation model, we will have to do domain like a fine-tuning stages. That will be basically adapting to the specific properties for the Detroit area traffic situation. Yeah.
What I was asking about, so the large language models take a long time and they use a lot of billions of connections. So once they train them, they kind of fix them. But if you have external data, usually people have their private external data, or
Yes.
there is a region. There's methods now that you can use this external data to go through the external data, then talking to the LLM. And I was thinking about, have you looked at that impact? So once I train the large language model and I fix it, and I have external data that I'd like to use, so I can do the forecasting better for this region, I might be able to get better forecasting.
Yes, yes. So that's the fine-tuning process that I mentioned. Yes.
Thank you.
Professor Liu, thank you so much for your insightful presentation. I learned a lot, and also very much appreciate your overview with the foundational model for time series and some of the trends associated with foundational models. I have a comment, and also I have a question. My comment is really, you mentioned traffic light optimization. We do a lot of these in our own group. I think it will be interesting to see how your thoughts on traffic light optimization through large language models and making predictions, and also connect that to the traditional traffic engineering practice and how we do adjustment to traffic light system. And so this the comment really, I think it's called for closer collaboration between the traffic engineers or the domain expert together with computer scientists. I see a lot of opportunity in terms of this collaboration. My question is really related with the predictive power for foundational models. Many of the transportation applications is related to predicting, I would say, either the accident or incident happens, and for example, whether there's a potential applications through time series to predict in terms of through vehicle trajectories to predict the conflicts or predict the accident occurs on the road. And so from time series perspective, from the foundational model, what do you think of the capability of this model to predict such, it's rare events, it's not regular normal driving situations?
Yeah, thank you, Henry. So to your comment, yes, I would really love to collaborate with experts in transportation. That's what I started to do about, I would say now 7 or 8 years ago. Really love to set up new collaborations as well. And then to your question, I think this is a really good question about there are a lot of, I would call this black swan events, in either the transportation system or in financial domain. They really care a lot about this particular rare actually incidents. I would say that currently we do not have a really good solution for that particular approach, for that particular challenge, because fundamentally that means that we have to look into consideration, take into consideration of external factors and that we do not see. So when we look at the reason that why we want to look at the so-called causal factors and causal modeling is because of that. So in this causal analysis, we basically will constantly consider and we'll have to consider the situation, the so-called external confounders. That means that there's something that happening outside the system that the event will play a role and play probably a major role in the changes of the whole system that we're looking at. And then the current approaches to handling the external factors is that we model them using different type of approaches, treating them as hidden variables so that we explicitly model the relationship between the confounders and with the input observation. The current technique is still relatively premature. That's why that I mentioned we don't have the best solution yet. But sometimes we do look for traces. For example, in the financial domain, the things that we want to look into is the text data. For example, either the news data or sometimes it's social media, tweets data that possibly consider some traces of the evidence of the confounders. And then with that, we'll be able to take into consideration. For anything that that we cannot take into consideration or do not have any traces, it's really a very hard problem. I think it's probably not what the current machine learning model can address. But still, that sometimes that in many areas that we actually do risk minimization. That means that whenever that we just consider there possibly be cases like this, and when we see that there's actually potential cases like that, then how do we minimize the risk instead of naively taking the predictions, because that's hopefully will help with the remedy, I guess, the black swan events, that for things that we cannot control and we cannot predict really accurately, and we just have to devise different type of risk control minimization step to handle the situation. Yeah.
Well, that's all the time we have, so please join me in thanking Professor Liu for their time.
Thank you.
So now we have a break until 10 a.m., and then we'll enter our first breakout, which includes a panel on transportation accessibility and a research presentation on electric vehicle charging station locations. Thank you.